Welcome again. So in today's lecture we are discussing about the percent S character. So percent S character is directly proportional to the bond strength and inversely proportional to the bond length, and it is also directly proportional to the vibrational stretching frequency and bond angle. So to understand what is percent S, we uh, we can speak that percent S file means those who attracts percent S character more. So triple bond, a double bond and a lone pair will provide percent S character, and percent S non-file are electronegative groups such as chlorine, fluorine, bromine, iodine, CF3. These are electronegative groups, so these are percent S hater, or we can say it oppose the percent S character. So the order or the priority order of percent S character will be like this: triple bond, then lone pair, then second bond, then double bond, and then the single bond. So let's take an example of bond angle comparison. So we know that it can be any metal or anything, and a B is present, and same from all this direction. If a triple bond is present with nitrogen, so we know that the percentage character here will be more, and in these molecules percentage character will reduce, and in lone pair it is a little less in that, and here it is non-existence. So if we talk about the bond angle order, so the bond angle will be maximum in here, and then in beta, and then in alpha. Why? Because of the repulsion between these, so this bond angle will reduce. Now let's take an example of NH3 and NF3. So we know that presence of this fluorine group, these are percent as hater. So the bond angle here will be, and the bond angle here will be bond angle order will be alpha is more as compared to beta, and same as we can say the percentage character will be more in alpha as compared to beta. So this is here. And for the next question, if we have an oxygen and H2O molecule here and a NH3 molecule here, so due to presence of these two lone pairs, the bond angle between this beta is less. So alpha will be more order of the bond angle, which is the order. And now let's talk about the next example. Here we have a hydrogen and hydrogen and hydrogen and hydrogenate tetrahedral structure. So this is the alpha angle we are talking about. If and this is all the fluorine are present, so there is no change in bond angle. Why? Because all the atoms are same, so there will be no reflection or anything. So this is tetrahedral structure, and both are equal structure. So now let's see some important points, which are these. If percent S is directly, if percent S is increasing, then bond angle will also increase and bond length will decrease. So bond length is inversely proportional to percent S character. For example, if this is the example, as you can see, it's a D1 and this is a D2. If a fluorine is present here and hydrogen is present here, so we know that fluorine is a hydrogen percent S hater, so carbon-carbon bond will be increased, and percentage character order will be D2, and D2 is greater, so this will be more in the distance as compared to D1. And if we talk about bond length, so this is the percentage order, so bond length order will be inverse. So D1 is more, so this is more D1, the bond length is more as compared to D2. So this will be the answer of these questions. Now let's talk about the next topic, which is NBEPR. So what is NBEPR? So it is referred to as non-bonding electron pair repulsion. So here there are some conditions for NBEPR molecule. So the condition will be the central atom or the main atom will be small. So central atom small should be small, and the side atoms, these are side atoms, side atom should be large. This is the condition for NBPR. So uh, due to NBPR, the bond angle between, due to presence of this reflection, so bond angle will between these will be increase. So this will increase, bond angle will increase due to NBPR. So this is the example, as you can see here, repulsion. So what we have studied in the previous slides, these are the summary of all that. So for bond angle calculation, we first need to check hybridization. So let we first need to check hybridization, and then whether the molecule is Drago molecule or not, and the order will be sp is greater as compared to sp2, and the bond angle order will be sp3, and Drago molecule will be the last, or as we can see 90 degrees the Drago molecule here, and sp3 it will be 180 degree, and this will be 109 degree. So this will be 120 degree, and this is 109 degree 28 minute. So this is the bond angle, and after checking hybridization and Drago molecule in the compound, next we need to check if the sp3 hybrid if the sp3 hybridized molecule has NBEPR or not. If it has, then bond angle will increase. After that, we need to check the number of lone pair in the central atom. More the number of lone pair, smaller will be the bond angle due to repulsion factor. So as we can see here. After that, we need to check the electronegativity of side atom. So bond angle is inversely proportional to the electronegativity of side atoms. The more the electronegativity of side atom, bond angle will be increased in NH3 molecule as compared to NF3 molecule. This is the example here. After that, the electronegativity of central atom. This is the last thing that we need to check for calculation. Electronegativity of central atom. So bond angle is directly proportional to the electronegativity of central atom. These are the also important points which we need to remember. Now let's talk about the geometry and shape. So for calculation of geometry, we need to check the bond pair and lone pairs of the atoms and molecules. And for the shape of the molecule, we only consider bond pairs. So what's a lone pair and what's a bond pair? So as you can see in these examples, let's take an example of CH3. So if we talk about geometry, then it has a tetrahedral geometry, and if we talk about shape here, it is tetrahedral as well. But in case of NH3, due to presence of this lone pair, and we can see it has 5 unpaired electron, so 2 lone pair and 3 bond pairs are present. So as we have studied before, so it has tetrahedral geometry. And if we talk about shape, so for calculation of shape, we only consider bond pair. So only 1, 2 and 3 bond are considered. So it has a trigonal pyramidal structure. So this is the trigonal pyramidal structure. And if we talk about this H2O molecule, so its geometry is also tetrahedral, and its shape will be, because of the 2 lone pair present in oxygen atom, due to oxygen have 6 unpaired electron, so it has a bent or a V shape or an angular shape. So these are all the names we can speak about this molecule. So for calculation this, we first start with steric number, then we can calculate the hybridization, and then we talk about its geometry, and then we talk about the shape. So there is no relation between the geometry and steric number, or hybridization and shape. We first need to calculate the steric number, and we go through this for this order according to finding all the shapes and geometries. So here are some example, or we can say the steric number calculation on the hybridization in which they belong, and the steric number and an orbital involved. So these are all the orbitals, SPDF and whatever these are. So these orbitals are involved in the hybridization, and their geometry is given. So Here in case of sp, its steric number is 2, so the hybridization will be sp, and its orbitals involved are s and pz molecule. Pz orbital are present, and its structure, its geometry will be linear. If the steric number is 3, then it has sp2 hybridization, and it has s1s and px and py geometry orbitals, and it has trigonal planar geometry. And if you talk about steric number 4, it has sp3 hybridization, and it has tetrahedral structure. And if you talk about steric number 5, it has sp3d molecule hybridization, and here two orbitals can be involved. If dz square is involved, then it has trigonal bipyramidal structure, and in this dx square minus y square is involved, then it has a square pyramidal structure. And if you talk about stack number 6, it has sp3d2 structure hybridization, and it has dx square and dx square minus y square and 3 p's and 1 s orbital, and it has an octahedral structure. And stack number 7, it has sp3d3, stack number 8 sp3d4, and these are all the orbitals involved, and their geometry will be for stack number 7 and sp3d3, it has pentagonal bipyramidal structure geometry, and for 8 stack number and sp3d4 molecule hybridization, it has dodecahedral geometry, and dodecahedral geometry for dx square minus dz square and dx square minus y square, it has square antiprismatic as a geometry. So after knowing about all this, we came from the next topic, which is the determination of hybridization. These are determination of hybridization. So we have studied in our early classes, it is just like same. So there are two methods, or we can use two methods for two types of molecule in which we determine hybridization. First, just like this, if a structure is given and we need to calculate its hybridization. If a structure is given and we need to calculate its hybridization, and another one, just a molecular formula is given, just like ClF2 plus or XCF2, and we have to calculate its hybridization. So these are the two types of determination method by which we can determine hybridization. So it is structural given method, and another one is molecular formula. So for calculation the number of hybridization or steric number, we count the number of sigma bond present in a carbon. So if you want to calculate the steric number of this carbon, then we can count the number of sigma bond plus lone pairs. So number of sigma bond plus lone pair, so it will give you over the steric number. So for this carbon, the number of sigma bond will be 1 2, and it is pi for the double bond. 1 pi and 1 sigma is present, so 2 sigma bond plus how many lone pairs are present in carbon. So we don't have any lone pair for carbon, 0 will be there, so 2 is the steric number, and its hybridization will be sp, so it is sp hybridized. And again, if you want to calculate the hybridization of this carbon, then its hybridization will be number of sigma bond here is 1 sigma from this, 1 sigma from this hydrogen carbon bond, and 1 sigma from this one. So there will be 3 sigma bonds are present, and its hybridization will be sp2 for 3 carbon. For 3 sigma bond will be sp, for 3 steric number it will be sp2 hybridization. Now let's get back to this important molecular formula method by how we can calculate molecular formula. So we can use two methods. First is cross-cutting method, and another one is by using a formula. Steric number is equal to 1 upon 2 the valence electron of the particular atom plus number of monovalent atom present in this in minus cation plus anion. So this is the formula for calculation of molecular formula or hybridization here. So let's take an example first and it will be more clearer. Let's take an example of FxCF2. So we know that according to this formula 1 upon 2 V, the number of V represent here is valence electrons of XCF2. So we know that if in a periodic table this boron, carbon, nitrogen, oxygen, fluorine, neon. So this is the periodic table and we know that है ने R K R N. So this is the last period or 18 period. This is the, so here it is 13 group. So here 3 unpaired electrons are present. This is 14 group, so there are 4 unpaired electrons are present. This is 15 group, so 5 electron, 16, 17, so 7 electrons, 6 electron, and 18, 8 electrons are present. So here if we talk about number of valence electron in Xe, so it will be 8 plus monovalent atom. So what are monovalent atom? Monovalent atom are atoms which connect with our Xe bond with single bond. So these are called monovalent atom. And there are bivalent atoms such as oxygen or sulfur. These are bivalent atom which form double bond. So these are not count. So monovalent atom, yeah, just like F2 is monovalent atom. So how many are present here? It has 2 monovalent atom and there is no charge, so we do not add anything. So now let's calculate this equation and we will get the answer 10 upon 2, which is equal to 5. So the steric number 5 for XCF2 molecule. So its hybridization will be sp3d for steric number 5, and its geometry will be trigonal bipyramidal, or it can be an octahedral or square pyramidal. Now there are another method to which we can determine or solve this easily to calculate its steric number, that is by cross method. So what is this cross method that we're talking about? So let's do this cross method with the help of an example, just like let's take an example of SOCl2. So these are the example, this is the example. Let's do this with the cross method. So we know that it is a sulfur molecule. It belongs to nitrogen oxygen family. So after oxygen, sulfur is present. O C T. So of sulfur, it has six. It has 1, 2, 3, 4, 5, 6. So it has 6 valence electron, and oxygen will form a double bond. So 2 bond can go for oxygen, and 1 chlorine, and 1 chlorine, and 2 are remaining. So it will be a lone pair here. So to calculate the steric number, we count number of sigma bond. So here it is sigma, it is sigma, it is sigma, and a lone pair, 1 lone pair are present. So to count this, we will get 3 plus 1, which is equal to 4. So hybridization of SOCl2 will be sp3. For site number 4, it is sp3. So this is the method in which we will calculate hybridization. So there are some exceptions or there are some exception method in which we do not want to apply this method. So where not to apply this method. So this method is not applicable for some of the molecules. So first will be when central atom is transition element. So if a transition element is present, so this method is not applicable here. We calculate this with a valence bond theory method. So next will be if a Drago molecule is present, then we do not calculate hybridization. And third will be when odd electron species are present. So just like that, when we just like ClO3, if we calculate it, it will be 1 upon 2 or 7 are present, so 3.5. So it will never be point. If it get a decimal, then this is not applicable here. And let's talk about the fourth one. When more than one central atom are present, just like example C6H6, so here it is also not applicable. Now, and the last one is when steric number is greater than 7, then it is not always the right answer. Sometimes it gives right, sometimes it not. So these are all the where not to apply this method.